Hello, my name is Trevor Ablett, and I'm a PhD candidate in the Space and Terrestrial Autonomous Robotic Systems, or STARS lab, at the University of Toronto. Today I'm going to be presenting Seeing All the Angles, Learning Multiview Manipulation Policies for Contact-Rich Tasks from Demonstrations. My co-authors are Daniel Yifan Zhai and Jonathan Kelly, also from the STARS lab. End-to-end visuomotor manipulation can be seen as an alternative to the traditional sense-plan-act paradigm that has been a staple of manipulation systems for decades. In this setup, we have raw visual observations, possibly combined with easy-to-acquire numerical state information, as well as actions that can either be raw joint commands or task space commands that leverage inverse kinematics, along with a gripper command. The key difference between this method and sense-plan-act is that a policy, often a neural network, is trained directly using these observations and actions. This is accomplished largely through one of two methods: reinforcement learning, in which experience is acquired autonomously and a handcrafted reward is maximized, or imitation learning, in which an expert provides demonstrations of correct behavior and a model is trained either offline via supervised learning or online via an interactive scheme. In this work, we focused on offline supervised imitation learning, sometimes known as behavior cloning. We were interested in answering the following question: will these policies work on mobile manipulators if the base location and viewpoint changes even slightly? To answer this question, we collected a human expert dataset of multiview data and trained it with supervised learning. After training, the multiview policies had significantly improved performance over policies trained with an equivalent amount of fixed view data in the multiview setting. As well, feature analysis revealed that multiview policies learned features that could consistently refer to the same parts of a scene through temporal and pose changes. For clarity, we'll start by defining tasks T as either TM or TF for multiview and fixed respectively. Both TM and TF can be considered as technically separate MDPs with a shared observation/action space, but different distributions of possible observations. Fixed view observations are generated via manipulator state and object state, while multiview observations also include variation in base state. Throughout this video, we'll refer to PyM as policy trained on multiview observations, and PyF as a policy trained on fixed view observations, where, unless otherwise specified, the tasks for each policy always match. Since manipulator state and object state are shared, and our observations are generated from the same sensors in each task, we can test PyM and PyF in both multiview and fixed tasks. Naively, we would expect PyF to perform poorly in TM, which we verify in our experiments. However, given the same amount of training data, we may also expect PyM to perform worse in TF than PyF because it must learn more information. Specifically, it must learn correct actions for observations generated by varying base poses, in addition to the correct actions for the single view at TF. The naive assumption ignores the effects of shared information. Specifically, there is non-zero task-dependent mutual information I between the expert action distribution given two different base poses, alpha and beta. In fact, if I was 0, a multiview policy wouldn't be able to generalize between base poses at all, which we experimentally show not to be the case. The question is I large enough, in a general sense, for PyM to perform well in TM and comparably to PyF in TF with an equivalent amount of training data? If this were true, it would imply that there was no detriment to training PyM over PyF. We can make a task-specific hypothesis based on general values for I. In cases where I is high, such as this lifting task on the left, PyM may provide little benefit over PyF when the base moves, because randomizing the object pose alone can provide enough information to complete the task regardless of the viewpoint. In this case, beyond the changing shadow positions, multiview data won't be significantly different from fixed view data. In cases where I is low, such as this hypothetical obstructed lifting task in the middle, it could be very costly to learn PyM, and it would definitely suffer compared to PyF in TF. In cases where I is somewhere between these two extremes, such as this door opening task on the right, we would expect PyM to be the most useful. Any case where it is difficult or impossible to randomize the pose of task-relevant objects, or where the background scenery changes even slightly between views, may be a good candidate for PyM. Because our method assumes that a separate policy generates base poses, we developed a scheme for autonomously generating base poses such that task-relevant objects are in view of the sensor and within the reachable workspace of the arm. All that is necessary for this is reasonable calibration between the base and the onboard sensor, a desired workspace center point, a desired max and min angle to set the base to, and a rough localization of the base between episodes, for which we find wheel odometry is more than sufficient. As shown in the diagram on the left, we generate poses along an arc around the workspace center, in this case directly in front of the door, and add a small amount of random noise to increase robustness in the policy. We should also note that none of this extra information is required at test time, or even at collection time, as it is merely useful for conveniently generating new training poses. The video on the right shows what our expert data collection process looks like on our real platform. You can see that the end effector tracks the expert's movements, and between episodes you can see the base changing from one pose to another autonomously. We generated several tasks for this work, in which we use both a PyBullet simulated and a real version of our mobile manipulator. The primary reason for having a simulated version is because it makes evaluating our method significantly less costly. Our observations contain raw data from an RGBD sensor, end effector pose given by forward kinematics and relative to the base, finger position of the gripper, and on the real robot we also use the force torque data at the wrist. The actions contain 6 degrees of freedom velocity, which is again relative to the base, which is then supplied to the joints using standard inverse kinematics, as well as a binary open-close signal for the gripper. As shown on the previous slide, we collect demonstrations using a standard virtual reality 6 degrees of freedom controller, and we add a simple compliant controller using the force torque sensor on the real robot to make it less sensitive to collisions, as well as using basic proportional haptic feedback using the controller's vibration motor, which we found to be necessary due to the level of contact and precision required to complete our tasks. We tested our method in the 7 environments shown on this slide. For each, between episodes, we vary the base pose and initial block/cylinder pose. For environments where the initial object pose cannot be varied, we instead vary the initial gripper pose, because otherwise the fixed base policies could learn to complete only a single trajectory, which would further hamper them in the multi-view case. Each of these videos is shown at 3 times real time. One notable benefit of our method is that we only require 15 to 30 minutes of actual robot interaction time per task, although the actual collection time on the real platform is generally a little bit higher to accommodate environment reset time. The architecture that we use for our policies is a hybrid convolutional neural network with a fully connected network head. It is inspired by work from Zhang and others, with some small modifications detailed in our paper. Notably, the CNN finishes with an attention-like mechanism called spatial soft argmax, sometimes just called spatial softmax, that extracts 2D feature points before concatenating them with other numerical state information and passing it through the FCN. Later on, we'll show how we analyze these 2D features to better understand the differences between multi-view and fixed-base policies. We train these policies with simple mean-squared error and no other auxiliary loss functions. Here we show the results of testing PyM and PyF on our 7 tasks. The main conclusion here is that in tasks with high mutual information, as discussed, PyM provides less benefit in the multi-view environment, although even in stack, it does perform slightly better than PyF. The real benefit shows up, perhaps unsurprisingly, in environments where we cannot randomize task-related objects' initial poses. As we had hoped, multi-view policies are either not or only slightly penalized in the fixed-view tasks, meaning they're effectively able to share much information between views. Due to the high cost of running PyF on the real robot, specifically because it fails and crashes into the environment often, we only ran it on door real, though we would expect the results of PyF in pick and insert real and drawer real to be similar to those in door real. We also note the relatively low success rate but high variance of pick and insert real. This is unsurprising given how challenging this task is, and empirically, even the failures here were near misses. Here we show our door reel task from 4 different angles, along with the corresponding sensor data used in each run. Take note, especially, of the large difference between handle positions between the top left and bottom right sensor data, and how different the arm trajectory must be to accommodate this. Here we show the results of our out-of-distribution experiments. We can describe our base poses using the scalar angle of their position around the arc previously described. In simulation, our training bounds were between -0.6 and 0.2 radians, or about 45 degrees total. We tested this angle an extra 0.2 radians, or about 11.5 degrees, in each direction beyond the bounds of our training distribution. We tested each policy in our multi-view environment for 12 different angle ranges, as shown in our plots. We note that PyF was trained exclusively at b phi equals 0, which explains why performance tends to be highest near that value. Even though the fixed base policies have non-zero success rates away from 0, the success rate drops dramatically compared to the performance at b phi equals 0, meaning that they haven't learned to generalize. In comparison, the multi-view policy performance stays relatively high throughout the distribution, and even out of distribution, with a noticeable negative skew. The negative skew is because of the right-facing angle of the camera, which, as b phi decreases, makes the scene more and more obstructed and significantly different from other views. Finally, we examine the spatial soft argmax features learned by both PyF and PyM in TM. We start by looking at the fixed space policy, PyF. At the top, we have 5 different angles or episodes of our door sim task, where we also show the highest activating feature that showed up on the gripper at least 80% of the time. In these 5 different angles, we also show 5 sequential time steps of an executing policy, starting 1 step before the gripper is initially closed, attempting to grasp the door handle. We generated these images by taking the 2D features and projecting them into 3D space using our known intrinsic camera model. It is clear that there is a relatively high degree of spread for this feature between time steps and episodes, which, admittedly, may not directly correspond to poor performance, but indicates that the feature does not consistently correspond to a single part of the image. Here we show the same, but for the highest activating feature on the door instead. Again, this feature does not consistently show up on the same part of the door. Here, we repeat the previous display, but now including the top 3 features on the door and the top 3 features on the gripper. Now we switch to the multi-view policy on the same 5 initial conditions of the door sim task, again starting from 1 time step before the robot first closes its gripper. Note how, with the exception of a few outliers from one episode, the point is relatively consistently indicating the same side part of the gripper, displaying less spread than the PyF features. We show the same analysis for the highest activating feature on the door. Apart from a few outliers, the multi-view policy has learned to consistently associate this feature with the same top portion of the door handle. Again, we show the top 3 features on the door and the gripper, but for the multi-view policy. While there is some spread for one of the gripper features, they generally have significantly more consistency than the fixed space policy features. Finally, we show a comparison between the feature distributions from PyF and PyM, where the difference in spread becomes much clearer. In conclusion, we posit that when training visuomotor manipulation policies, if one can move the base, it will be almost always beneficial to do so. We note that this benefit is quite similar to the benefit achieved by domain randomization, where the environment is randomized between episodes or time steps to generate a more robust policy. We showed that this strategy not only performs suitably well in both multi-view and fixed-view scenarios, but that it generalizes to out-of-distribution data and implicitly, without any enforced loss, learns more robust features. For future work, we're interested in algorithmically generating data from other viewpoints, which has been shown to be possible in the domain of view synthesis, but it is currently unclear how one could also generate the corresponding correct actions to take from these simulated viewpoints. Solving this problem could dramatically reduce the cost and time of generating policies that can generalize to multiple views, and it also may improve performance. Thank you for watching our video on seeing all the angles, learning multi-view manipulation policies for contact-rich tasks from demonstrations. My name is Trevor Ablett, and I'd like to also take a moment to thank my co-authors Daniel Yifan Zhai and Jonathan Kelly. You can see more details from this work and all the other cool stuff that we do in our lab at starslab.ca.